Okay, so good morning, everyone. So welcome to come to the tutorial on bias and fairness in NLP. I'm Kai-Wei Chang at UCLA, and I have Vincente here. And unfortunately, Meg cannot come here, so we have Fino to give a talk about her part. And today we are going to cover several parts about the fairness in natural language processing. So Fino will first give an overview and discuss the cognitive bias and data bias, also the bias laundering in the machine learning. And then I will talk about some bias in the NLP application and what can we do to try to mitigate such a bias. And then Vincente will talk about the fairness and robustness presentation for the vision and language. So then we can talk about how to debias in the multimodality model. And finally, we will have a conclusion and have some discussion here. So without further ado, let me turn the mic to Fino.
Alrighty. Hi everyone. My name is Vinod, and as Kai-Wei was saying, Meg could not make it here, unfortunately. So I have stepped in to sort of like give the talk that she had already kind of like prepared. And so I work with Meg at Google Brain in a team working on ethical AI and machine learning fairness. And so we work on similar stuff. And like, so today's talk, it's going to be like an introduction of like various kinds of sort of biases that exist in our data sets that we use to train our machine learning or NLP models, and how those sort of biases has a tendency to sort of like feed back into the data that we later might be using. So a phenomenon that we call like bias laundering. And this, the content that I would be talking about is, has contributions from a large number of people within Google and outside of Google. So this is like a long list of people, and this is also not exhaustive. There's many other collaborators who have actually contributed to much of the content that I am going to be talking about here today. I will start with setting up some expectations for, specifically for my talk and also like the tutorial in general. That we will be talking about, as Kai-Wei said, we'll be talking about a general motivation for fairness research in NLP, and how NLP models may be unfair, and why they might be happening. And we would also discuss, especially Kai-Wei and Vicente would be talking about various types of, digging deeper into various types of fairness issues and mitigation approaches that we can apply to sort of address them. And we would also have some sort of recommendations on what we can and should do. This talk would not be giving any definitive answers to fairness and ethical questions, because those are still, there's a lot of open questions there, like what does fairness mean, and like, so those sort of questions we won't be kind of addressing here. And also, we won't be giving prescriptive solutions to fix machine learning or NLP unfairness. By that, I mean, we might be discussing a lot of solutions or sort of like approaches towards sort of specific NLP fairness issues that can be addressed through specific methods, but that doesn't mean that that's like a, you know, we can apply that to like sort of like to fix all the NLP fairness issues. So it's something that we think is something that we need to keep in mind all the time, and sort of like be mindful about it and be cautious about like the models that we are building. Having set up that sort of context, I will start with a small exercise. If you have seen the slides from Meg's presentation somewhere else before, please don't answer. But looking at this, what do you see? Anybody? What do you see here? Bananas, several bunches of bananas. Some people might be seeing stickers in those bananas. If you're from the United States, or like a place where Dole bananas are, like, I mean, the brand is there, you might recognize that those stickers are Dole company. You might say bananas at a store, bananas on shelves, bunches of bananas, like you said. But we don't tend to say yellow bananas, right? But if you see this picture, you usually say green bananas or unripe bananas or raw bananas. if you see this, we will say ripe bananas or bananas with spores. But we tend to not say yellow bananas, even though bananas are like more often yellows, or like at least the bananas in like the West is mostly in yellow, or at least what we eat, buy from the stores. And that's because yellow is very prototypical for bananas. And the idea of being prototypical or prototypicality comes from, or like it's been studied under like the prototype theory, where it sort of like goes down to like our purpose of categorizing objects is to reduce the infinite differences among stimuli to behaviorally and cognitively usable proportions. So in that process, there may be some central prototypical notions of items or objects that arise from like stored typical properties of an object category. And we tend to sort of like lean into that and like sort of make that implicitly assumed when we talk about or when we mention things in our day-to-day interactions. There are exceptions for that, of course, but usually the basic level, there's like, bananas are supposed to be yellow, and like, so you don't really explicitly call that out. And I start with banana, but let's move on to something else. Another small sort of like test. It's like a little story. A man and his son are in a terrible accident and are rushed to the hospital in critical care. The doctor looks at the boy and exclaims, "I can't operate on this boy. He's my son." How could this be? Like, what do you see any inconsistency in this narrative? Anyone? Like so this is like a question, it's kind of like a trick question that has been asked to a large number of people, and like some people say, well, it could be that the kid has two male parents and like, two dads. That's possible. Any other explanations? Excuse me? Yes, and I think you said the same thing. But it's great that it's great that I have that answer from here, and it's a case that it's a female doctor. But this was a study that was done in, I forget, Boston University a few years ago, and a significant number of people could not come up with that as an explanation. And that included, and to go back to the prototypicality of this, because like prototypically we think of doctor, when somebody says doctor, you just assume that it's a male doctor. And if it's like a female doctor, you actually qualify it with a female prefix. And the study was done, and as I said, in Boston University, and the majority of test subjects, it's done by a psychology, in the psychology department, and the majority of test subjects overlook the possibility that the doctor could be a woman, doctor is a she, including men, women, and even self-described feminists. Like in the test subjects, they had those sort of information that was collected. So it kind of like talks about like the kind of implicit biases that we ourselves have, but also in terms of like how that would be reflected in the data that we are collecting and using to train our NLP models. Another one more example here is in terms of like just counting the frequency of words in like a large corpus. If you just look at it like, the word murdered occurs like 2 million times in this particular corpus, compared to like blinked occurs like 390,000 times, or breathed like 700,000 times. It doesn't mean that we murder people more often than we blink. So that's what is called the human reporting bias, that the frequency with which people talk about or people write about stuff, like actions, outcomes, and properties, is not really a reflection of the real world frequencies of the degrees or the degree to which a property is a characteristic of a class or individuals. So this is, intuitively, it's something that nobody would object to, but just tie this to the fact that we use the coreference metrics as ways to like calculate, say, word embeddings, and all sorts of like NLP tools use sort of like counting these kind of frequencies to make sense of words and make meaning representations and so on. So it's important to keep in mind that these sort of biases exist in the data out there, and think about how that might be affecting in the models that we are building. So this is one sort of like bias, as I said, reporting bias. And that would affect the training data that we are collecting and annotating for our purposes. And then a typical machine learning pipeline or an NLP model training pipeline uses this data and annotations to train a model. That model then such models would be used to filter, rank, aggregate, and generate new data. And that would then, and people would see that output. And this sort of like is the sort of like the pipeline that is usually happened. And the biases that exist in the data, and there's all sorts of different kinds of biases that exist in the data. And I only talked about the reporting bias. So far, I've been talking about just the top part of that long list of biases, meaning the reporting bias. But there's all sorts of other kinds of biases that might be creeping into our data sets. And I wouldn't go into every single bias here, but in the next few minutes, I'll go through like a few examples of these like other kinds of biases, not to define them and like go into depth for them, but just to give examples to sort of bring them up to the surface. And specifically, I'll just go into these ones: reporting bias, selection bias, outgroup homogeneity bias, confirmation bias, overgeneralization, correlation fallacy, and automation bias. So for selection bias, so I already talked about reporting bias. For selection bias, one example is the case that we use a lot of a lot of NLP work is done in English data. That itself, there's like a huge bias there. Like a lot of NLP research is done using English language, and many times we don't even mention that. We just if it's in any other language, that we actually explicitly mention, but we don't usually mention that it's in English. But even within English NLP, is the data that we use to train from for training our English NLP models, are they representative of all the Englishes out there? And you can actually, imagine that the British English is going to be different, slightly at least, from the American English. But if you compare that to the kind of English spoken in in African countries or in India, those are significantly different from the U.S. American English. And later in the talk, I would talk about an example of how that might actually result in problems. But for now, I'll move on to another instance of selection bias. That let's say that we have sure, we have moved on from let's just say the U.S. American English is what we are going after. But even within that, we have or there has been studies that has demonstrated that in the data, there is a huge gender bias in whose data, who's creating, or whose language is actually represented in this online data. Men are overrepresented in web-based news articles. Men are overrepresented in Twitter conversations. And there's also gender bias in Wikipedia editorship that has been documented. Only around 12 to 15% of Wikipedia editors are female. In other words, a large amount of the Wikipedia data that is out there are probably written by male editors. So when we use Wikipedia data to train, models, large models that we use for NLP models, such as the BERT language models, are we actually training English, or are we training the male English, if there is one such thing? And social linguists have over the decades have studied and demonstrated many instances that shows that men and women use language differently. So it's possible, and this is something that has to be empirically studied, that it's possible that the BERT language models, or the language models that we are training on, sources such as Wikipedia, might be superbly biased towards one particular gender. And that's one example. And another one is we use mechanical Turk annotators for getting annotations for many of our tasks. And this is sort of a distribution of where these Turkers are coming from. And if you look at it, you see that there are clusters that actually contribute to this workforce. And so think about all the kind of biases that are coming in there. There's cultural biases that are going to be creeping into the labels that we are obtaining. And sure, I think people who are obtaining the annotations have of late recognized this and incorporated that into the training procedures, but it's something that to be mindful about, that in a different culture, things that we are something is something considered as negative may not be considered negative globally. And the out-of-group homogeneity bias is like, I wouldn't go into detail, but you just kind of like, if you see the figure, you kind of get a sense of like what that bias means, and this is more relevant for, say, like when you're obtaining labels and stuff. And these kind of biases, like the reporting bias, sampling bias, out-of-group homogeneity biases, these also would result, it's not just about like the representation, but also the biased data representation. So even if you actually have a really balanced data set where we have approximately the same amount of sort of like representation for each subgroups that you care about, even then, you have to be mindful about what if like some groups are represented less positively than others within that data set. And an example that I'd use is like, say, in a corpus that that contains like discussions about actors and actresses, if you analyze and if it turns out that, let's say if it's like from some online forum, comments that are made on an online forum, and if the comments, if it is a case that more often female actors or actresses gets comments that are like relatively more negative or relatively more sort of objectification and like all sorts of other sort of like gender biases that people exhibit, and then those comments would basically result in having like a representation bias that gets propagated into the kind of models that we use that data to train for. It could also result in biased data labels, and this is what the example that I was talking about, the out-of-group homogeneity bias, maybe is playing a role here. This is annotations in a data set that are reflecting, that captures or sort of like put keywords or like captions on images. And whoever is labeled this data, like looked at these pictures, and the first two pictures they recognized it as a ceremony or wedding, whereas the last one they did not recognize it as like a ceremony. It's just like person, people. So that kind of nuances are lost when you don't have like a culturally diverse like annotation pipeline. So moving on to biases and interpretation, and this I'll go relatively quickly. So confirmation bias is something that you probably have heard of already. We have a tendency to search for, interpret, favor, recall information in a way that confirms pre-existing beliefs. And it's also amplified in the case of like when we have search engines that gives you the results like that are like superbly sort of that aligns so much with like the things that you're searching for. And if you're going to search with keywords that actually align with like what your original opinion is, you're going to see articles that are also aligning with that opinion, and you would miss out on like things that are like countering that opinion. So that's one example of confirmation bias, but of course this happens in research as well. Overgeneralization, coming to a conclusion based on information that is too general or not specific enough. Like if a dog just thinks that like all cats have 4 legs, I have 4 legs, so therefore I'm a cat. I mean, these are like, if you think a little bit, like you could think of examples in our research, in our papers that we actually have made this error ourselves. And the last one, correlation fallacy. And this is another thing that, again, we often make, that when we see associations, we sort of make the leap that it actually is causation, but it's not always the case. And this is the example of women's voting and also the world wars. And I don't think that actually there's a causality relation, but that there is correlation. And in our analysis, like when we use NLP, we are actually going by most of the time, it's the correlations that are getting like baked into our models to make predictions. I mean, those associations are essentially correlations. And finally, automation bias, which is a documented or demonstrated sort of bias that humans have, that the propensity for humans to favor suggestions from automated decision-making systems over contradictory information without automation. So this is, for example, if I'm like a content moderator, like I'm going through like a platform, comments made on a platform that tend to be like, my job is to actually tells or like ban or like take down comments that are toxic or whatever. And there's already like tools that do that, like using machine learning. And if a machine learning algorithm has said something like is toxic, then would I override that and like say that this is not toxic? And so this is like one example, and like there's all sorts of different places where like human in the loop kind of like settings where a machine already predicts something and then the human would make a judgment, and it has been demonstrated that the human judgment would then be biased, or there's a high likelihood of like that human judgment being biased by when a machine makes a incorrect prediction. And there's all sorts of different experiments that people have done on like what level of information is revealed and whether that has an effect on the human bias and things like that. So, I mean, that was just like a very high-level picture of this like different biases in these two different axes. But biases not just happen in data. It also happens in like different phases, like how we decide to train the model, like what objective function we decide to actually optimize for, how like media is filtered, ranked, all these product deployment decisions, and also the people would finally see the output, and then that would result in like a feedback loop of like putting that error, that kind of like biased perspectives being propagated into the world, and that would then lead into having like this data being fed back into our models, and like this is what we call bias laundering. Like, so bias already existed, and we basically had this machine learning model that kind of like takes it and like sort of like recycles it and sometimes amplify it. And I'm gonna talk about it in a minute. Just jumped ahead. So we talked about bias so far, and I talked about all sorts of different biases. But is this bias really bad? And before I go further, like, let's just make sure that like I'm not talking about the bias in the statistical or machine learning sense, the bias of an estimator or the bias term in our like objective function, or the cognitive biases, even though I talked about a lot of cognitive biases that would result in like biases in the data, but that's not what I'm talking about here. I'm specifically from this point on, I'll be talking about algorithmic bias, which is basically talking about the unfair, unjust, and prejudicial treatment of people related to race, gender, income, sexual orientation, religion, and other characteristics historically associated with discrimination and marginalization when and where they manifest in algorithmic systems or algorithmically aided decision making. And that's sort of like the frame that we are going after here when I talk about bias from here onwards. And that was also put forth like very nicely by this in this Guardian article. Although neural networks might be said to write their own programs, as in like super intelligent, they do so towards goals set by humans using data collected for human purposes. If the data is skewed even by accident, the computers will amplify injustice. And for me personally, I think the amplification of injustice is like a much bigger problem. If the data, I mean, there's already injustices that exist in society, and that's going to be reflected in the data. But how much does our machine learning models have a tendency or like have a potential to amplify those injustices and make already marginalized people further marginalized in terms of like their or how they harm, how it harms them? I'm again jumping ahead. I'll get there in a minute. So before I go further, I will go through some case studies of fairness or unfairness issues in machine learning and NLP. In machine learning in general, most of it has NLP components there. And then I'll go into the more sort of like high-level details of how we address the sort of like think about fairness. So the first case study that I'm using is about language identification. Most NLP models in practice, in most of the industrial kind of applications, has a language identification step. It may not be explicitly marked there, but there's usually a language identification step that like you have a piece of text, it goes to a language detection, and if it's not in a language that you support or you have a machine learning model trained for, you actually throw it down the bin because you don't have the capability to process that, right? You know, so, and if it's like it's, and that's what you use it for, like the further analytics or whatever. And how well do these language identification systems do? In 2005, there was a paper published in the Computing Sciences in Colleges Journal that basically claimed that the paper describes how even the most simple of these methods using data obtained from the World Wide Web achieve accuracy approaching 100% on a test suite comprised of 10 European languages. So they basically called language identification a solved problem. Right, and it is true. In most in 10, 15 years ago, in most sort of like benchmark tests, like it was approaching like 99% accuracy or 100% accuracy or whatever. And you could think of this being used in a public health monitoring example, where like you have this kind of like you want to monitor like all the tweets coming from like different parts of the world, and like monitor sort of like people mentioning say flu-like symptoms, and then using that as a way to sort of like get at like parts of the world or parts of the country or your country where there might be a flu outbreak. Let's say a hypothetical use case of like using this public health monitoring. And I bring back the sort of selection bias issue, or like the world English situation here, right? And a paper that was published like 2 years ago at Jurgens et al. In ACL showed that language identification on aggregated works like 99% accurate, but it performs so low for tweets that are English tweets, tweets that are in English that originate from certain countries. And they correlated that with the Human Development Index of that country, and they found that the less developed a country is in terms of like the Human Development Index, the more likely the less accurate the language identification system is. So English tweets originating from countries like Nigeria and India has a very low performance on this off-the-shelf language identification system compared to like tweets that are originating from the US or Australia. And what does that mean? It means that people who are originally, who are the most marginalized, the people who actually could be benefiting from, because especially in India's case, like there's all these villages where like, you know, these sort of like technologies or socially good applications of AI could have like huge benefits. People who are already most marginalized, people who would benefit the most from these kind of technologies, are also the ones who are more likely to be systematically excluded from this technology, because the language identification system is not tested on tweets that are coming from that geography, for example. And so this kind of like a unfairness issue of language identification systems were never sort of like thought about, tested, or that was not even like in the sort of like mindset of like people who were designing these systems. And so this was like a hypothetical scenario, but you can imagine like this being applied to like many other applications where this might be happening. The second, oops, did I do something? I did. Wrong button. Another example case study that I would talk about is there was this paper, I think, yeah, again, a couple of years ago from Stanford that said that deep learning neural networks can more accurately than humans detect sexual orientation from facial images. And they have this like sexual orientation detector that they trained using images from public profiles in the US dating website. And they basically try to tie it back to like some sort of like studies in like medical sciences on this. And there was, I think there was a lot of backlash against this study, questioning why we should even consider this study. Why should even like we build, just because even if we can build a accurate system to do that, like is that something which is ethical to do? So that's not the question I'm going after here. But later there was a follow-up article by Meg and her colleagues that basically showed that the differences between the lesbian and gay faces in that data set relate more to grooming and presentation and lifestyle. Like if you put like makeup and like certain kind of glasses, that was enough to actually make a distinction between like, or switching the label from like gay to straight, or like lesbian to straight female. And that was a case of like, the sort of like this confirmation bias at play, and also the experimenter's bias there. Another example is about predicting criminality. So there's a couple of examples here. So there's an Israeli startup that claims that they have a proprietary computer vision and machine learning technology for profiling people that reveals their personality based on their facial image, and that could be used to recognize high IQ, white-collar offender, pedophile, and terrorist from face image. So this is like a startup that I mean, they haven't published any of these, any scientific sort of like studies or like any empirical results on like the evaluation or anything. So we don't even know what technology they're using. But there's this other study that was published in 2016 called Automated Inference of Criminality Using Face Images. That Wu and Zhang, so they used wanted suspect ID pictures from like specific regions and like built this like deep learning tool that can predict, that they claim that can predict criminality. And one of their findings was, for example, that the angle from the nose tip to the two mouth corners is on average like smaller for criminal than for non-criminal. So this was one of the findings. And this was published and everything. But then Meg and her colleagues wrote this piece, I think the next year in Medium, basically shows that it's just a difference between frowning and smiling. So when criminals, like, if you're taking a mugshot of someone, you're more likely to be frowning or at least not smiling. And that's the difference that you're actually capturing, not any sort of like physiognomic sort of like characteristics that I was talking about, like criminality. So this is another example of like, confirmation bias. And we might, so I think these two examples that I used are like not NLP per se, but like you can think of these sort of like examples happening in our NLP research as well. But I use these because these are like the most commonly discussed ones in recent years. And finally, I'm coming back to NLP, which is predicting toxicity in text, is another case study. Here, I'm going to be using an example from Jigsaw. Jigsaw is a sister company of Google, and I work with a lot of folks there. So toxicity classification is this, so they have a engine or toxicity classification engine called Perspective API that is used by various publishing platforms out there, including New York Times, The Guardian, Wikipedia, and so on, to look at like really offensive content that is online and sort of like and how they use it is like different depending upon like the publisher. Like they may use it as to censor the comments, or they may use it to rank for like reviewing them by a human moderator and so on. And that we don't have access to like that, how they do it necessarily. And the toxicity in this particular case, I mean, even the question of like how do you define toxicity itself is like a loaded question. There's a lot of ethical questions around it and fairness questions around it. But here in this case, they define toxicity as a rude, disrespectful, or unreasonable comment that is likely to make you leave a discussion. They started doing sort of like this bias analysis on these toxicity models probably 3 years ago. And there was this paper that they published in 2018 that showed that the toxicity model that they had in production at that time had unintended biases towards certain identity terms. Things like if you say, if the word gay occurs in the sentence, that kind of shoots up the toxicity score to a high value. Similarly, transgender or the term Muslim. So these are, you can imagine why this might be happening. I don't have like empirical proof for that, but one is that in a lot of online forums, the word gay is often used as an abuse, like you're so gay, or like, that's such a gay thing to do, or what, like, there are like usage of the term gay in in abusive gay, lesbian, and transgender in like in that context, but also it might be discussed along with a lot of this toxic content. Like they may be talking about like bad things about this identity, the people with this identity, and similar case with like the term Muslim as well. So that kind of like context, that like kind of toxic context that exists in the online comments gets captured as like the meaning of that word and gets propagated into this toxicity classification challenge. And this is my hypothesis, and I haven't proven that, but that's probably what is happening. But like what they did was they had like some really good methods to rectify that, and their current production models do not have that bias, or at least the bias is mitigated. And in recent work, well, this is work that I will be presenting in 3 days at the last session in the main conference. So show up for the talk, where we look at, or where we have shown that there is unintended biases that can happen towards like named entities. Here, if I say I hate Justin Timberlake, it's labeled as like more toxic than like I hate Rihanna. That's probably because somehow the word Justin has acquired this like sort of toxic meaning, and that is getting propagated. And there are many other people's names that you could probably think about that I'm not going to be talking about, who also has these sort of strong toxicity biases in this model. And another paper that just got published 2 weeks ago at the the accessibility conference, where we looked at how various biases towards mentions of disabilities happen. So if I say I'm a person or I'm a tall person, it's not a toxic comment at all. But if I say I'm a blind person or if I'm a deaf person, the toxicity score goes up. And this is like the current toxicity model that we are using. If I say I'm a person with mental illness, it gets like a really high toxicity score of 0.62. Well, not really high. I mean, it's not 0.92 at least. But like, so these sort of biases do exist still, and it's the one thing that to note here is that we have to actually look for the kind of axes that we're interested in to actually find these biases. So you could kind of like fix this one issue, but like then there will be some other axes along with like our model might be biased that we don't know about. So always we have to be like kind of keeping in mind about these kind of biases. So NLP research on bias and fairness, like so that what has been happening within the NLP research field, and that's what like the tutorial is about, right? So this is last June I gave a tutorial on fairness in NLP around June 2018. I gave this talk, and this was my slide where I went into depth of like these 3 papers, and then. Now, or like a couple of months ago, I was looking for the same slide, and now it has basically grown to this like more than almost a couple of dozen work that has gotten published just in the last year and a half. And this is not even all of it. Like this is just like a subset of it, and I'm not like this is not exhaustive by any means. So this kind of is just to show that this is a field that is like extremely sort of volatile and very active research going on. So anything that we talk about today, just like take that with like that context, that like this is not like a solved problem. This is like an area that like there's active research going on, and that makes it more exciting to actually be talking about. And one of the common themes of many of these works is about like looking at whether social disparities or injustices or stereotypes are getting captured in word embeddings, for example. That's one of the main themes that happen in that kind of work. And there was a work by Kaiwei and Vicente and other colleagues that kind of like triggered this work was computer programmer, man is to computer programmer as human is to homemaker. That was published 3 years ago, 2016. So this is like, this has been documented in like various other kind of like dimensions of like socio-demographic subgroups. And so one of the questions that people might, just to mention, so Kaiwei and Vicente would be going into the depths of those papers and like actually talk about like how do you look at these biases and like how do you maybe mitigate them and so on. But one of the questions that people ask when we talk about these kind of biases is like, well, I mean, but aren't they just like reflecting what's there in the society? And this is like in line with what I said earlier in the talk as well. They are just like reflecting what's the injustices that are out there in the society. And it's true. If you actually do a correlation study between the word embedding bias on gender in the y-axis and the women's occupation difference on the x-axis, you know, it seems to be correlated, sure. This is like a study, again, published in 2018, where they looked at the gender bias in like word embeddings and kind of like correlated that across different decades. So here, each of these squares are sort of like calculating the correlation between that particular year and the other decade. Sorry, this is like they collect this like 100 years worth of data or like textual data and trained word embeddings on each decade granularity, and then compared or like correlated the calculated the correlation between the biases that exist in one decade versus the next decade. And so the diagonal is like all perfect correlation, but if you look at the first like 1910s, the kind of biases that exist in the data from 1910s to 1920 is like 0.7, very high correlation, right? But it also, one interesting thing that you can actually notice there is that in the 1960s, the kind of bias, the gender bias that exists in the public discourse that is measured in this like data set changed. So from till 1960s, there was like a certain kind of gender bias. They are kind of correlated together. And then from 1960s onwards, there's like a different kind of gender bias. And that just happened to correlate with the women's rights movement in America. And they had a similar kind of analysis of other kind of like social movements that are reflected in this data. There's also sort of like, you know, bias towards like the term Asian with adjectives that are, so in adjectives with words that are like closely related to outsider. So it's, you can kind of roughly think of this as like in the US sort of like language or text that is collected from the US kind of context. The term Asian, so the bias that is expressed in this text towards like Asians, people of Asian origin, has like that kind of like a bias towards the terms outsider, like is kind of like dropping over the decades. Sorry, this is the wrong figure. There was a different figure that had this like bias going up towards like the tourists. Sorry. Anyway. So yes, so aren't they reflecting the society? Yes. Word embeddings are getting things normatively wrong precisely because they get things descriptively right. But then the question is, shouldn't we then just leave them as is? Like, you know, some people argue that like we should just like leave them as is because it's just like what's out there. And like if you go de-bias in like some way, then like we don't even know what kind of like other kind of biases we are actually introducing. But then the follow-up question is, would that harm certain, if we just leave it as is, would that harm certain groups of people? And then we would have an issue. And one example, I wouldn't go into details of many different examples that Vicente and Kaiwei will be talking about. One example is like recently it was shown that AI hiring tool that was penalizing resumes with word women's in it. And this is like something that was actually probably happening through, you know, the term women's have this like negative association with someone getting hired or something. And so this is like, you know, this is one example, and there's like many other examples of like actual harm caused. So the question of harm is like something that we kind of like have, you know, we intuitively know what we talk about there. But in 2017, Kate Crawford put this like kind of like a framework to think about different harms caused by machine learning models, and we can think of that like for NLP as well, called allocative harm, or you can think of it as in terms of allocative harm and associative harm. The allocative harm deals with situations where a system is allocating or withholding a certain opportunity or resource from people, and having a machine learning bias, having a bias that actually goes into that system would result in certain groups or marginalized groups have like their access to allocation to resources gets sort of like or gets affected, gets impacted, right? And you can think of situations like the toxicity model, for example, is a situation of like allocative harm because it's encroaching into your right of free speech. You can think of the occupation classification thing because if that's going to be used for routing resumes to resumes of job applicants to job postings, then that's a problem because if that results in like showing certain kinds of job ads only to females and certain kinds of job ads to males, that's actually going to propagate and even amplify those kind of issues. And there's already empirical studies that have actually shown or demonstrated that issue. Associative harm is a more sort of subtler but more important maybe kind of harm, where these kind of systems result in reinforcing the subordination of certain groups that already exist in that kind of subordination already exists in the public discourse or in society. And our machine learning models like propagate and reinforces that issue. And those are the kind of, like you can think of like the word embedding biases that we are actually looking at, like could be thought of as like an associative harm. Like, you are propagating models out there that actually represents what it means to be sort of as a person with mental illness, with like associating that with like toxicity and negativity, which I would say is an associative harm. So it's important that we measure and try to mitigate algorithmic fairness or bias issues. And in order to do that, one of the very easy and or like sort of straightforward and important ways to actually address that is to, like, when we do evaluation, do disaggregated evaluation, like rather than go with the majority, always think about the subgroups of people that we care about within that context at least, depending on where this would be applied or whatever. Because we can lean on like the studies that already exist in the world to see who are the marginalized people in that kind of like a setting. But you could also find ways to detect new sort of discrimination axes, but like at least we know already existing discrimination axes in like the kind of product areas that we are going after, and then create different subgroups and prediction pair, and then compare the performance across different groups. For example, like how well does face detection do for men versus women? There's also calls for intersectional evaluation. That is, we have to create different subgroups for like the intersection of these subgroups, and that's important because it's very, when you look at it, it looks very trivial. But this is like from a legal standpoint, there's like a precedent of this story of I think it was GE. I think there was a female worker who was working at GE, I believe, like in the 1800s, went after like for sort of like I think 70s, went after for like the I think accusing that the GE had like bias against like black women, and the court ruled that no, GE does not have bias towards black women because there's a lot of factory workers who are black, and there's a lot of like secretaries and like sort of like workers in the offices who are who are female. So there cannot be any bias, and that was like the court ruling. But it turns out that like GE was hiring only white women in the secretarial positions and black men only in the sort of factory workers kind of position. So black women just like never get into that kind of like roles, and that kind of like I think the idea of like discrimination or like how it was like read was very different back then, and that has changed since then. So I think when we do evaluation also, it's important to like sort of just not look at gender alone and like race alone, because when you intersect these things, there's like different axes of discrimination that might be happening in our models that we don't know about. And these are just things that we all know about, as in like, when we evaluate models, we have false positives, false negatives, true positives, and true negatives, and we have like these metrics that depending on like how we are reporting them, like we have recall, precision, negative predictive value, false positive rate, and so on. And you could look at like equalizing any of these metrics across different subgroups depending on the use case. So just a couple of things that I will talk about here. For example, you could argue, or you could try to equate or like sort of make sure that like you have equal recall across different subgroups. And that kind of like an intervention is called equality of opportunity fairness criteria, where we actually try to ensure that or sort of like change the objective function or training process or whatever to see that we have equal recall across different subgroups that we are considering. We could also look at predictive parity fairness criteria, where we are trying to sort of like make sure that like we have equal precision across different subgroups. And these two should be applied depending on what use case that we are going after. For example, in the case of, say, privacy in images, if you're actually building a model that blurs images like for privacy, to preserve privacy, then false positive is something that doesn't need to be blurred. Like, you know, if something that doesn't need to be blurred gets blurred, sure, it can be a bummer, but like it's not like such a big deal. Whereas false negatives could cause harm. Like something that needs to be blurred is not blurred, that could result in identity theft. So we may want to equalize the false negatives there. Right, across different subgroups, so that like we can be sure that we are not harming any single subgroup unfairly or sort of like disproportionately. Similarly, in the case of spam filtering, if you get an email that is spam and that is not caught, like so you see it in the inbox, usually it's just a bit annoying, but beyond that there's no big issue. You may actually flag them as spam next time. But if it's like a false positive, that is the email is flagged as spam and is removed from your inbox, and that could be problematic, especially if it's like an interview call or like information about your family or close friends or something. So in this kind of scenario, false negatives might be better than false positives, and you have to actually optimize for false positives, like, or not optimize, rather, like try to equalize false positives. So you have to choose which metric you actually try to equalize across different subgroups based on the actual problem and how or what harm it might cause to people. So with that, I will, I believe, conclude soon. So in summary, AI can unintentionally lead to unjust outcomes, and that's what I've been talking about so far. And lack of insight into sources of bias in data and model could result in this. It's also caused by the lack of insight into feedback loops that actually kind of propagates and reinforces many of these things. And also in the evaluation techniques, we often take the majority, or whatever, the global evaluation metrics is what we usually go after, and that's not always sort of giving you the fuller picture or richer picture that is important to take care of in these kind of situations. And also human biases in interpreting and accepting the results and publishing the results. So what do we do? And that's what Kaiwei and Vicente would be talking about. I think Kaiwei is going to take over and talk for another half an hour. Sure, yeah. While he's, oh, you don't have to split. Yeah, sure.
So you showed some examples of toxicity.
Sure.
What I would imagine is a negative with negative makes some positive. So like discrimination inherently is negative, H is negative, but if I say I hate discrimination, that's a positive statement.
Yeah.
So do the models capture this kind of?
I mean, the challenge with negation is like a very age-old NLP problem. I think it happens in many of the NLP systems. I think that's a very hard problem, and I think I haven't explicitly went after that specific question, but I think the more recent NLP models do a much better job at it than maybe 5-6 years ago. So sort of modeling if you train a bidirectional SDM, it might be capturing the negation or the in that kind of context and flipping the meaning and stuff. I don't really have a clear sense of how much does that happen in the toxicity situation.
I'll just take 1 minute to quickly explain where I'm coming from. So it's very interesting that there are a lot of cultural differences in how we perceive this kind of things, right? So let's say in India, a face of a god, Hindu god, or face of, let's say, Mahatma Gandhi on a doormat or lingerie is considered extremely negative. Whereas the face of Abraham Lincoln or the US flag on the doormat is not a bad thing in the US.
Yeah.
And this is precisely because, let's say, the positive, Abraham Lincoln or Mahatma Gandhi are very positive in their respective countries. But doormat is not negative in the US, whereas doormat or something to do with feet is negative in Indian culture.
Yeah.
So this kind of things are, I mean, this is a real problem. I'm from Microsoft, and detecting that becomes an issue.
No, absolutely. I agree with that wholeheartedly. And I also, I mean, it's not just like doormat. Like, I personally cannot step on like a piece of written paper. Like, that's like so culturally, I've learned like that's like such a no for me. But that's not a thing like in West, right? So yeah, culturally there's all these differences. And I think one of the biases that I talked about was like when I showed the map of annotators that we have, like, and how that's like clustered around like 3 or 4 like geographic areas. I was referring to like the cultural kind of like concentrations there, and like so the labels that we're getting might have like these kind of biases baked into it. And it's not that like one is right or the other. Like it's about like us being aware of like the fact that these differences exist and these differences needs to be accounted for. And to kind of more concretely respond to it, I think I know of, I haven't personally come across situations like that, but I know that like at Google there were annotation cases where like they had to do separate training to actually have the annotators like culturally sort of like I wouldn't say cultural training. I mean, for the annotation purposes, like telling certain, giving specific instances and showing that like this is okay in this context, and like so sort of like doing that translation process was one of the ways that it was addressed in like I think years ago. I don't know which product or whatever it was, but I know that such training process is like one way to actually just like do that cultural translation. But I'm not saying that like that would just like fix everything. But yeah, it's a real problem, which usually we don't think about or talk about. Any other questions? I mean, we also have like a good 15, 20 minutes at the end to have a discussion. So yeah, sure. Will be?
Oh, yeah.
It will be. They will be. Sure. All right. I will hand over to Kevin.
Thanks. Okay, so in the next 15 minutes, I'm going to give a review about several studies in bias in NLP and how can we to control this kind of bias. So of course I cannot like go over all the works because there are so many awesome works in many different subfields of NLP are talking about the bias and fairness issue. So I will only focus on a partial of them. And some work done by the whole community and also some work done by my group. So here is a subset of my collaborator that have a significant contribution to this. Okay, so let me start with a cartoon of the NLP pipeline. So I think this is most people in NLP area know what we are doing. So we usually collect the data, and then we usually train an encoder or something that we learn the representation and to get a feature from those data. And then we have a decoder to do some downstream tasks. Like we're trying to make a prediction, we're trying to predict like path tree or whatever we want. So then after we got a prediction, we would design a evaluation matrix. And most people using like average over the whole test data set and to trying to see how the performance of the model we design. And nowadays we also use a lot of auxiliary data. So we got a wood embedding, we got a bird contextualized embedding, all these encoder that train on a large data set and put into our system. So that can improve the performance of our model. But it's also, when you consider the fairness and bias issue, then those biases can come from everywhere. So it comes from the training data. It comes from this embedding model we used. And when we learn such a representation, then the representation may have a bias. And the algorithm we use may also enhance the bias. And so then we got a bias in our predictions. So it turns out when we do the evaluation, if you only look at the average performance of your model, you may say, oh, this is an awesome model. This is a superhuman performance. But if you do the analysis on the result you have, then you may see that the model may perform well on certain kind of data, but perform pretty bad on the other type of data. And of course, this is not a new issue. This is an issue like a domain adaptation, and also a lot of the issue we have been discussed in all the time. But when it comes with the notion of ethic and fairness, then we need to think about what is the implication of our results. Okay, so let me use a coreference resolution as a motivated example. So back to the NACO last year, there are a few papers talking about the coreference resolution model has some bias. So as we know, coreference resolution is basically we want to identify all the reference to the same entity. So for example, if I give you a sentence like this, the current state of the model can easily identify the pronoun his is referred to the president here. So if we do a simple change that we change, so if we do a simple change, we just change the male pronoun his to the female pronoun her, then you may think the model should give you exactly the same prediction because this is basically not changing anything there. However, if you look at the result of the model, then the model now cannot identify the pronoun her is referred to the president. So of course, this is a cherry pick example. So we also do a more systematic study. So we build up this data set we call the window bias data set. And there is another paper by Rachel also built another similar data set like this. So basically, we're using this window grand schema that we create two sentences, and each sentence contains two occupation words. And one occupation word is historically people know is still typical to the male, and the other occupation word is to the female. Then we create a sentence like this: the physician hired the secretary because he was overwhelmed with clients. And the other sentence is like the physician hired the secretary because he was highly recommended. So as you can see that the pronoun he refer to the physician and also refer to the secretary depends on the content. And this is a pretty difficult coreference resolution situation because you cannot just using the syntax and to guess what this pronoun referred to. And you really hope the model can learn from the context and trying to figure out what is the pronoun referred to. Okay, so and then we have these two data. So we call the data set that when you have a pronoun he referred to this stereotypical male occupation as a stereotypical data set, and the other data set is anti-stereotypical. So now we just change all these male pronoun to the female pronoun. And again, we didn't change anything there, so the model should make the similar prediction when you do this swapping. And as you can guess, that the current state of the model, but also different kind of correct model, all have a bias. So when you evaluate on these two different data sets, one data set get a performance like a 75, and the other get lower than 50. So this is using this F1 score that people usually to analyze the coreference resolution. So as you can see, there is like a 20% gap between these two data sets, and the average is about like 59. Okay, so this show the correct system has a bias. So the question is there a way that we can somehow train the model in a different way so the model don't have such a bias? So over the next few minutes, I will talking about how we can do that. So let me just show you some result first. So if we debias the word embedding that using in this correct system, then you can see the gap becomes smaller. And if you're also trying to do something on the training data, here that people use the Kono data set to train the model, then you can see the bias is almost go away. And then we'll talk about that how can we do this in the later of this talk. Okay, so before I go to this technical detail, let me went back to talk about a more high-level question that how this bias come to this model. So let me first let's first do some exercise. So let me ask this question. So which word is more likely to be used by female? So anyone want to make a guess? Is giggle or laugh? Okay, so people say giggle. Okay, and then let's guess. Which word is more likely to be used by old person? Yeah, impressive, right? So why do you intuitively recognize this kind of social group by the word they use and by the thing they write? It's because we have a kind of implicit bias, right? And when people write and when people talk, and there is a certain kind of way that people talk differently. And when they generate this kind of data, it's back to what Vino was talking about, that those data will have this kind of implicit bias. And this implicit bias is hide everywhere. It's from the word choose, it's from the content they talk about, it's also from the grammar structure, and basically it's hide everywhere in the data. And just review what Vino said, that in the Wikipedia, if you analyze the demographic of the editor, then you can see that a large portion of the wiki page is written by the male students, actually. So the Wikipedia actually reflect what they are thinking, and also the topic of the Wikipedia page is also selected by those people. So that means that there are less extensive articles about women and about the topic that care by the women. So this is a study they done around 2010-11, but now there is a movement in the Wikipedia community that they're trying to enhance those topics that care by the women. So things can get improved, but you know, as a community of NLP, we cannot wait until they fix the problem in the Wikipedia. We should do something about that. Okay, so back to our topic. So because the data are biased, and this is not only in Wikipedia, but on all the online contents, on even on the books that people write, and we all have this kind of bias. When you train a model using this kind of data, then you will expect the model will also have a bias. So sometimes these biases are not bad, but for some application, this can show something pretty bad. So for example, Emily will talk about, give a talk in this EMNLP about, she analyzed the bias in the language generation systems. So we analyzed the sentence that generated by this GPT-2 model, and if you give a prompt, and then this is basically what the GPT-2 model generate. So I don't want to read this, so you can read it by yourself. But as you can see, that when you give the word like the black man or the white man, then you generate a different kind of content. And of course, this result showing here is kind of cherry-picked, so there are more systematic analysis that Emily will talk about in her talk. So here I want to talk about where the bias is and how can we deal with that. So most specifically, we'll focus on this representation bias, like how the model represent all these concepts differently for different gender or different group of people. So this back to the paper we have in 2006 that we're trying to analyze the gender bias in the word embedding space. So in that time, we did a very simple but interesting things that we're trying to see what is a representative pair that the model can generate if I give the model a direction of a gender. So as we all know, like in the word embedding model, we can take like two words and take the difference between their factor and then somehow represent some direction of some concept. So for example, if you give a word like he and she, if you give a word like man and woman, then this pair will somehow represent the gender. So we generate like the, we basically give this direction to the model and ask the model to give me all the representative pair that the model thinks that can represent this gender direction. So it's not surprised we got a lot of good analogy pair like brother to sister, like uncle to aunt, like king to queen, but it also gives you something crazy. So it gives you beer to, anyone want to guess? Wine? Yeah, wine is a good guess. And the model gives you beer to cocktail. So this is cute. It's not a big deal. But if you think about the occupation, the model gives you physician to registered nurse. And model also gives you professor as an associate professor. And also like associate professor to assistant professor. Yeah, so basically the model ranked all these peer higher than some peer that we know should be represented as a gender. So that is a problem. And there's another science paper that do a more formal study using the implicit association text, which is the well-known text in psychology, like trying to test the implicit association that the people are thinking. So, so let me first discuss how people perform this test, and then I will talk about how we apply this text to the word embedding model. Okay, so in the following test that they want to do is basically trying to see if the people have an implicit association between the gender and the subject. So the gender is represented by a bunch of a name of a male and female name, and the subject is represented by some subject related to science and the subject related to reading or literature. So the way they do this implicit associate test is like following. So first I will show you a words, and I will ask you to categorize this word to either to the concept of a boy or the concept of a girl. Okay, so this is pretty early in the morning, so let's do some exercise. So if you think this word is categorized as a boy, you can raise your left hand, otherwise you raise your right hand. Okay? So what is this? Okay, left. Great. Yeah, and how about this? Right, yes. Okay, and next we will do this, the same thing, but now we are thinking about the concept of math and the reading. Okay, so what is numbers your category to? Some people do left, some people do right. Okay, that's fine. And now we are trying to see if there's an association between the gender and the subject. So now I will show you two groups at the same time. So if the word is either categorized as a boy or math, then you raise your left hand. If oh, now I see the problem because we have a different direction. Then you raise your left hand. And if it is categorized as a girl or reading, and this is on your right. Okay, so how about algebra? Okay, how about Julia? Right, so everyone do this very quick and very nicely. So now I do the same thing. I still ask you to categorize the word to either to boy or reading or girl to math. But now I swap the reading and math. So then we can try this again. So how about literature? How about then? Okay. So as I can see from here, when we do this, boy and math in the same category, girl and reading put on the same side, people do it much faster than the other way around. So basically in this IAT test, they do this on the computer and trying to count your response time. They're trying to categorize all these words. So the finding is they find that if you put these two concepts that still typically associates concept on the same side, then people respond time is much faster than the other way. Okay, so this is for the human, not for the word embedding model or whatever NLP model. But we can borrow this kind of a way to analyze the implicit association to analyze the word embedding model. So in this science paper, the team from Princeton, they basically do this to trying to see if the word embedding model also present the same implicit associations as a human. So what they did is we consider, again, two groups of concepts. So one is a subject, another is a gender. And for these two groups of concepts, we get some representative words. Right, so here I use X to represent all these subjects related to science, and Y is all the subjects related to art or literature. And then for the gender, we also have a group of words represent the male, and the other group of words represent the female. And then we're trying to see how these words are associated with each other. And the way we calculate the similarity is using the cosine similarity. So basically, I'm trying to see if I give the word mathematics, is it more closer to all the words with a male concept or all the words with a female concept? So I get this average cosine distance to somehow represent the bias of the word mathematics. And I can aggregate these results. Then I will have this statistic to basically represent how these average association score for all the words in this math subject and comparing to the literature subject. So if the difference are large, means that the model embed more bias, and if the difference is zero, means that the model think all these associations are very similar. And from the statistic point of view, you can also compute the p-value and the effective size of the bias, but I don't want to go to the detail, so let me just show you what they found. So they found that we can use this test measurement to measure the association between the pleasant, unpleasant to a flower and insect. And as you can guess, that most people like flower, we don't like insects. So you can see there's a significant association between these two groups of concepts. And they showed that when we talk about the European American and African American to the concept of pleasant and unpleasant, then you can see a very similar trend. That the model also capture this kind of implicit association. And by doing so, then we basically can show that the model has this kind of implicit association, and we call this is a bias in the embedding model. Okay, so in the last few years, there are also many different studies like trying to analyze and show the bias in the word embedding. So let me just show you one more thing. So if you want to visualize what kind of gender implication of words in the embedding model, you can do the thing at the following. So you can first get several pair of gender that represent what is this gender direction, like he to the she, father to the mother, king to the queen. So this is all the definitional gender pair. And you can run this principal component analysis, and this will basically show you what is principal direction among all these pairs. And what we find is that they do have one strong component that represents this gender. And comparing to if you just randomly pick several pair of words, then the eigenvalue distribution will be something like what you see on the right. But if you deliberately pick this gender pair, and the eigenvalue distribution is like something on the left. So you can see that they do have one gender component in this embedding space. And if you project all the words to this gender direction, so the x-axis is this gender direction, and the y-axis here is basically random number, but we basically are trying to put the definitional gender pair that we know on the bottom and all the other words on the top. Then you can see that those definitional gender words are project to this gender direction nicely. So you can see like queen is closer to this she direction, and like brother is closer to this male direction on the right. But the model also categorized the word like a game is more closer to the male, and like dress is more closer to the female. So we hope the model can keep the gender direction for this definitional gender pair, but we don't want the model, to represent all the other words that should not have a gender components with this gender information, especially if you want to use this kind of model to some sensitive downstream application. Okay, so as I said, this is not only for the gender. This can be extended to analyze other kind of bias in the embedding model. So Yulia from the CMU and her team has analyzed using a similar method to show that there is a bias in the race group and also in the religious group. So the key difference there is that in the gender, especially in the previous study, people usually assume there is a binary gender. But we all know this might not be true. And also, if you want to analyze something like race group or religious group, then this is not just a binary, like two direction. Then their extension basically show that you can extend this to this multi-category situation. Okay, so this is about the English embedding model. So I guess people here may already have a question in your mind. How about other embedding model? Right, we know there are many languages beyond English, and we also know there are different kinds of embedding model that we can learn from the data. So here is another paper that Pei will present in this EMNLP, that he analyzed that what is gender bias in the language with a grammatical gender. So as we know, some language like Spanish, German, or French, we have this grammatical gender rule. That means that if you are talking about, so basically every noun will categorize into the feminine group or the masculine group. And depends on the group the word belongs to, you are going to change the adjective, the verb, and also some other form of association word when you mention those nouns. So for example, a car is a masculine word and motorcycle is a feminine word, and so the adjective and the verb need to change according to that. So if you run the same analysis I show you on this embedding model on this grammatical gender language, then there will be a big problem, right? Because every word is associated with a masculine or feminine group. And because there is a strong information for the surrounding context, so the model definitely will categorize the thing in the right way. But then in that way, you won't be able to tell the gender bias or tell what is the model actually trying to model the gender information, like semantic gender, I mean. So to deal with that, what he did is that he first trying to put all these feminine word and masculine word in this word embedding space, and we project that into this to this space so we can see that. And you can see that all the feminine words are grouped together on one side and masculine words are grouped on the other side. And we can try to learn a gender direction, the grammatical gender direction to categorize these things. But the problem is that different from the semantic gender I was talking about, you have a gender pair, like male and female, he and she. Here, what is the corresponding word to my motorcycle, right? It's just like a bunch of nouns that you cannot find this counterpart on the another gender. So instead of running PCA, as I described, he ran this linear discriminative analysis, which is a low-dimension projection technique that people use in this supervised data set, that we're trying to find that one direction that kind of categorize these two groups of the data. Okay, so with that, now we can project all the word to these two directions. So one direction is this grammatical gender direction that I just described. So this is on the y-axis. And the other direction is a semantic gender direction. Basically, again, you just pick a bunch of he and she and male and female and define that direction. And that we call the semantic gender direction. And interestingly, these two directions, of course, they are correlated, but they actually, the cosine similarity is that around 0.7. So they are correlated, but they are not identical. So you can actually project all the words to these two directions and see how they locate. So first, we can project some occupation words. And so this is a result on the Spanish. So every occupation word has a male version and a female version. And you can see that if you look at the y-axis, the model kind of categorized the feminine words and the masculine word correctly. So all the blue word is a masculine form of the word, and the red is a feminine form of the word. And you can see that they categorize correctly on this y-axis. But if you look at the x-axis, then you can see there is one word, the male version of a nurse, is actually closer to the female than other word closer to the male. And you can also project all the other common noun to these the two-dimensional illustration. So the word like perfume actually is a masculine word in Spanish, but we know it is more associated with female, and it also shows in this figure that the perfume on the semantic gender direction is closer to the female, but on the grammatical gender direction, this is masculine words. So Pei will have a poster at the EMNLP, and you can talk to him. He will show you a more systematic study on this. And let me just talk about one more thing before the break, that the similar analysis can be also used to analyze bilingual word embedding. So in bilingual word embedding, we know that we project the language, embedding with a different language into the sense space. And when you perform this projection, there is also embed certain kind of a bias. So again, the blue word here I show you is basically the masculine form of the occupations. And the red word I show you here is a feminine form of the occupation. And the gray word in the middle is English occupation words. So as you can see on this figure, that if you look at doctor, then doctor is closer to the male version of a Spanish word. And the word nurse is I don't know if you can see here. So nurse is here. So nurse is closer to the feminine form of the nurse in the Spanish. So this again showed that in the bilingual embedding space, the model has certain kind of implicit association, so that the word embedding is the position is located like what I showed. Okay, so let's take half an hour coffee break. And after break, I will show you more results on this direction.